Hello guys, welcome to Amazing Engineering, and today in this OpenFOAM tutorial we will analyze the wake effect between two cars. This phenomenon takes place every time two cars are lined up and involved in an overtaking. Because we have to follow the same way of the 3D wing case for creating the geometry and setting the boundary condition, I will leave you the video in the description and I will go a little bit faster. So I made as first the work directory, I called it wake effect. Then in SolidWorks I created the car geometry file, then I exported it as a step file. Inside Salon I imported the first car, the second car behind. I made a box around the cars in order to create the domain. Then I made the first cut operation, selecting the box and the first car, and at the end for the domain I made another cut operation, setting the first cut operation and the second car. Then I created the geometrical graphs for the boundary condition, so inlet, outlet, frontier, ground, car and second car. In mesh field I created the geometry, calling it car domain, and I set edge and 3D and 2D parameters as the 3D wing case. Then I imported the geometrical graphs inside the mesh and exported the mesh as a UMV file inside the work directory. So I opened a Bash Ubuntu window and I created the polymesh directory using the ideas UMV2FOAM command. In boundary file I set the type of boundary condition for each graph, so patch type for inlet and outlet, symmetry for the frontier, and wall for ground, first car and the second car. In transport properties I set the value of kinematic viscosity for the air. In turbulence properties I set the model to use during the simulation, in this case the K-epsilon model. In zero directory, in UMV file, I set a fixed value boundary condition for inlet, setting 8 meters per second, zero gradient for outlet, symmetry from the frontier, and no slip for the first car, the second car and ground. In pressure file I set zero gradient for inlet, a fixed value for outlet, symmetry for the frontier, zero gradient for first car, the second car and ground. In eddy kinematic viscosity file I set calculated boundary condition for inlet and outlet, symmetry for the frontier, and nut wall function for the first car, the second car and ground. In K file the turbulent kinematic energy. For inlet I set the value of turbulent intensity energy, setting 25%, zero gradient for outlet, symmetry for the frontier, K-wall function for car, and K-wall for car for the first car, K-wall function for the second car and for ground. At the end, in epsilon file, the dissipated energy. For inlet I set the value of mixing length, which is equal to 0.07 times the length of cars. zero gradient for outlet, symmetry for the frontier, and epsilon wall function for the first car, the second car, and ground. After setting the parameters of the simulation in the control.dict file, we can start our simulation using simple foam command. Moreover, if we open another version of Ubuntu window, we can watch the residuals during the simulation using foam monitor -L, post-processing, residuals 0, residuals point det. Thanks to this command, we can watch how the residuals vary during the simulation, and we can know if the simulation is converging or not. So, as you can see, simulation converged after around 300 iterations. Now we have to open ParaView with parafoam command. Click on Apply. As first, we could watch the streamlines around the two cars, so let's go to Filters, Alphabetical, Extract Block, and select the two cars. Now select a physical property, for example velocity. Change the color mapping, for example with blue to red rainbow. And start the simulation. For the streamlines, we have to click Stream Tracer. We can set, for example, X direction. And as a resolution, we can set 400 streamlines. Click on Apply. As you can see, the second car is left by less streamlines than the first car, so the drag of the second car is expected to be lower than the drag of the first car. In order to calculate the drag, we can follow the same way of the 3D wing. So let's extract, for example, the first car. Select pressure. Normally, for cars, car drag is calculated using the front area, so we have to make a clip. Set -1 as normal along X direction. Let's go to Filters again, selecting Extract Surface. Then generate surface normals, setting Compute Set Normals. Click on Calculator. We can call it, for example, Drag 1. Select Cell Data, call the array Drag. We have to multiply the pressure for the normals along the direction of motion, for in this case along X direction. Click on Apply. Now we have to integrate the values along the front area, so let's go to Filters, Alphabetical, Integrate Variables, click on Apply, select Cell Data, and this is the drag of the first car. For the second one, we have to follow the same way, so now we have to extract the second car. This is the pressure along the surface. we had to make a clip again. Select Extract Surface, generate surface normals, selecting Compute Cell Normals, calculator, we can call it drag2, select cell data, we can call the array drag again, and again we have to multiply the pressure for the normals along x direction. Then let's integrate the results, click on apply, and as you can see, the drag of the second car is lower than the drag of the first car. You can also import the results in an Excel file, and if you repeat the simulation increasing the velocity value, and you plot the result, you can get something like this. And as you can see, the drag of the first car is always higher than the drag on the second car. Okay guys, this is all for today. I invite you to subscribe on my channel and see you for the next video.